Why do we want to perform Z transform? There are many reasons. One of them is this: when we convert a sequence into a polynomial, then multiplication in polynomial is actually convolution. And this is why we get convolution in time is multiplication in the frequency domain. You can try it for yourself with simple multiplication of polynomials, and you'll realize that it is actually convolution in the original sequence. Second is that when we perform a delay in the sequence, then we are just doing a change of power in that sequence. For example, we have a sequence 1, 2, 3, and this is n equals to 0. Then the conversion into the Z transform is simply 1Z0 plus 2Z minus 1 plus 3Z minus 2. Compare this to 0, 1, 2, 3, where this is n equals to 0. Then this is actually 1Z minus 1 plus 2Z minus 2 plus 3Z minus 3. So if you compare the powers of Z, then we are just changing the power by, actually it is Z minus 1 times the original 1Z0 minus 1 plus 3Z minus 2. Now, if you actually think that this is a conversion of a sequence to a polynomial, then of course it's a lossless transformation, because we are representing a sequence by a polynomial. The powers of the Z represents the sequence. Therefore, everything else is the same. So there is no change of information except that we have just converted it from one representation to another, and therefore it is a lossless transformation. Now, then there's the other thing. It converts the sequence into a closed form equation. How? Well, especially for geometric sequence, we can convert it into a geometric series when we by Z transform. This is the original sequence. This is just a repeating pattern. This is just a pattern of numbers. But, well, when we use Z transform, we convert it into a series, because we are now adding the terms up. And when this series have a pattern like a geometric series, then it can be represented as a closed form solution. So we'll see this later on. Why do we like closed form solution? Well, I mean, this is a nice example. 0.333 is represented as 1 divided by 3. A much simpler, much more compact representation than 0.333 forever. What are the reasons? Well, later on you will see that when we perform Z transform on the impulse response, so what is Hn? Hn is, this is Hn, so we send an impulse, so this is delta n, and then out comes y of n. Y of n is delta of n convolve with h of n, and remember delta of n is the impulse. When you convolve with h of n, it gives you h of n. So h of n is the impulse response. The Z transform of the h of n is very special. It is called the transfer function. And what is the transfer function? What is it? H of Z is actually a surface. So we'll see it later on, but I'll show it to you now. What does the surface look like? So this is the real part of Z. This is the imaginary part of Z. This is the 0. This is where the origin is. This is the imaginary part of Z. And in the vertical axis, it is h of Z. In this case, I'm plotting the magnitude, or the log magnitude in this example. Now, 20 log. Now, so once you have h, to get h of Z, you plot the h of Z in the entire Z plane. So this is the entire Z plane below. And for every value, you'll get h of Z. And h of Z is a complex number. And since the complex number have two values, we cannot plot four-dimensional. So what we do is that we plot absolute value of h of Z. And typically, instead of plotting absolute value, we plot 20 log h of z. So this is in the decibel format. So this example is we're plotting the 20 log h of z over here. And you see that it is a surface, magnitude surface in the log scale. And it will rise to infinity somewhere when there's a pole. And when they have 0, it will go down to 0. Okay, now with this surface, we can study where the peaks are and where the valleys are, and it will tell us the stability. Okay, and we can even guess the response when we have plotted the pole and zero diagram or the h of z. Okay, and finally, when we convert h of t to h of z, or when we convert x of n to x of z, we can use the z transform properties. We can guess the initial value, guess the final value, perform delay, manipulate difference equations, just like the Laplace transform, which converts differential equations to algebraic one. So here we convert difference equations to algebraic equations, and we can manipulate them. Okay, and multiplication, of course, multiplication in the z domain is convolution in the time domain. So these are the many reasons why we're interested in z transform.